Hello! Today I'm going to be playing with some of the different kinds of distance sensor. So distance sensors you can use on robots to measure how far something is away. Now I think you may have already seen me previously getting a Microview working with one of these distance sensors, and I've used them on plenty of my robots before. But what's interesting is today I've got a new type of sensor to play with, and this is the VL53LOX time of flight distance sensor. My goodness, that's a mouthful. I want to compare and contrast this device with this device. Now, I mean, there's first a choice of controller. Now, while ultimately it would be nice to get it working on a Pi, which is where my robots are mostly working, I'm going to do it with the Microview because A, I've already got the Microview working with these, and B, you get a nice visual display. Now, a Microview, if you've not used one, is effectively an Arduino with an OLED display built in. That means I think it is actually a 328 if you're familiar with the terminology. We'll get one of these working with it again, and we'll see the display, and I'll go briefly look at the code and the wiring, and then we'll do one of these, and then we'll talk about the advantages and disadvantages of the two types of sensors. I've taken off the Microview so you can get a closer look, and I've got the Microview carrier board here which shows which way it goes up, and it's also got the pin numbers on it. I've got a positive going across here to this breadboard line here, so there's my VCC. I've got pins 2 and 3 going across via these slightly ugly connections with these two purple wires, so that'll be the trigger and echo pins, and this will be ground. The HC-SR04 has 4 connections: VCC for your voltage, trigger which tells it to send a ping, echo which comes back after a certain amount of time with a ping, and then your ground. Now the trick with this is you actually have to, after triggering it, time exactly how long to the microsecond the pulse on the echo pin comes back. Let's plug this in, and we want to line it up so we've got something on the silk screen to say which way up it goes, so we'll line that up and drop that in there. And if that's VCC, this lines up going that way, so it's going to be detecting distance that way. And let's see if I power this up. So the display on it, and I think you've seen this in a previous video, is showing the distance of anything from that sensor. And the little tiny arrow there is actually showing the distance being read, so there's a number and a gauge, which makes that quite easy. And that means if we got multiple sensors going and we wanted to calibrate them, which I think in this video we're going to try and do, then we'd be able to put them next to each other on this display. So when using the Microview with the HC-SR04 sensor, this code, partially used code from the internet, and I've tidied up a little bit myself. So we've defined the trigger pin and the echo pin, that's important. And obviously you need multiple ones of these if you have multiple devices. We got some variables for duration and distance, although because they're actually in this one loop, they may have been local. So that's what you get when you get code from the internet. We set up the pin modes. This stuff here, UV begin, clear and begin, these are all about just setting up the Microview to display the output. So this is our Microview slider widget. So we've got our Arduino loop code here. So we go and do the trigger pin. So pulling it low, then high, then low again. That tells the HC-SR04, go and do your first ping. So now we do a pulse in, and pulse in actually counts in microseconds exactly how long it takes for a pulse to appear on this echo pin. And so when we get this high pulse on the echo pin, we get the duration. So we take the duration, we multiply it by this factor, these numbers here, to convert it into centimeters. We then set a value on the display to the minimum of 100, and that distance in centimeters. So if the distance in centimeters is above 100, it go beyond where our gauge is, so we don't want to do that. So we limit it to 100. and that means we've got a maximum distance in our code of 1 meter. I've also got some print statements here just to see it on the serial monitor in case some of the rest of this wasn't doing anything, so I can see what it did. I mean, this code isn't too fussy, it's fairly small. The only tricky thing here is you've got microsecond delays and you've got this pulse in. The Arduino is fairly good at this. This gets trickier with a Raspberry Pi, trickier with some of the other controllers.
So if you've been enjoying lots of my robotics builds and you'd like to build more yourself, I'm actually currently writing a book. The book will be available December 2018 or January 2019. The title is Learn Robotics, Fundamentals of Robotics Programming. And it'll be based around a Raspberry Pi with Python. I'll be covering basics around building robots and putting together a chassis, doing stuff with line following, distance sensors, odometry, that is speed sensors, and then even more interesting topics like speech processing and visual processing and controlling with a joypad. I don't only discuss the systems, tools and programs that I'm using, but I talk about why. I talk about how the decisions were made about this tool over this tool and why I chose things. So if you're interested, the book is actually on Amazon. It's already for pre-order, or you can wait until the actual time and come then. And if you like what I'm doing, this is a great way to see more. Before I can use these time of flight sensors, I'm going to need to solder some headers onto them. It's not a big job, but it's got to be done for each one. And you get a choice of a right angle and a straight edge connector. And I've been warned to be a little careful with these sensors because apparently the surface mount chips on the top can find their way off. So I've got 2 of these sensors. And there's another complication with these because I've also been told that they occupy the same I2C address. However, I've thought of that. This is the TCA 95488A I2C multiplexer. It means I can give one of these a completely different address from the other. And that looks great fun. I can see there are many SD lines, so maybe they all share a clock but all use different data lines. Is that right? No, there's different clock lines. Wow. 8 devices which may even have the same addresses. Presumably that means you could also simply multiplex your bus. And then these over here, and I find out which ones to link them with, but it looks like cut to disable the pull-up, so pull-up resistors. That's for the I2C buses to pull them up, so then you signal down to pull them down. And these 3 probably for setting the address line actually on the device. Very cool. I'll put that at about 300. And I can mount them facing that way into something. Kind of tricky, this one. Let's figure out how I can hold it. It's a very tiny device. Guess what I can do is wedge it just there on that top groove. Let that one set, and then we'll get this one over here. And the next one. Go with the same, so there. Oh, well, that's frustrating. Yeah, that is the way to do these. Clamp the connector. Leave the board loose. Didn't think that would work, but that actually made for a much... It's still not perfectly straight. I don't know which has come out straighter. The second one was far easier to do. Okay, now this actually, because this is not an outboard sensor, this could just be popped onto a breadboard. So I'm more than happy to make that one straight on. So the only thing I lament with these is I'm more than happy to solder, but sometimes I'm working with people who really aren't happy to solder. And so therefore they go, oh, well, I'm not going to use those sensors because I have to solder them. And on the one hand, okay, it'd be great to teach more people to solder, and I'm definitely up for that. But on the other hand, there is this feeling of, well, someone's taken the measure of breaking it out to a board that is through-hole, which is cool. But then there is, well, why don't they do just the one more step and solder them? I suppose they don't flat pack so nicely, because they pack nice and flat when they're not soldered. But, you know, it's the kind of thing I can imagine that the right people will just pay a small premium to go, you know what, I'll just have mine soldered already, thanks. Nice trick with tool-in line packages. You can use a breadboard to keep them nice and straight, and then you'll know that they'll be nice and straight for a breadboard afterwards. Drop that on. Like that. And then hopefully it won't be too tough to take off. Okay, now I'm trying to control this and control the board. Let's not be trying to control the board. Let's give myself fewer things my hands are doing at once. You just use that one there. Just give more weight around the breadboard, so the breadboard's not going anywhere because the breadboard was trying to slide away from me. That's class, isn't it? There we go. Job done. Okay. Well, we'll be able to use that in the experiments then. Let's get them breadboarded up. So I've brought 5 volt up to a 5 volt rail here and brought ground down. And then the A5 and A4 pins on the Microview are the clock and data lines for I2C. So we can then take our VLX and drop it right in. Now, I've got a little bit of a tab that's got to be peeled off. I'll leave that one. I've already done this one. And so we'll plug it in with the tab peeled off. Voltage in lined up and then ground lined up. So that drops in there nicely. And once again, we'll attach our Microview. Normally, when looking at a new device, I'd go through its datasheet and look for clues in the datasheet on how I'd write the code for this. And in the case of I2C, because I've already got a certain amount of experience with I2C devices, I'd be looking for the I2C registers. So I'd expect there to be perhaps a register that tells it what mode it would be in to start getting data. There is an interrupt pin, GPIO1. Okay, so I think that's an interrupt pin, and I think you could wire that up to your microcontroller and go, I've got data. So what I'm looking for in the datasheet are those numbers, some register addresses, so I can use those to communicate with it. We can see the headline, the world's smallest time of flight, ranging and gesture detection. And there's a bunch of blurb here about what the sensor can do. And I think what we really want to find, so let's have a look at the table of contents. Technical specification, system block diagram, well that could be interesting. Okay, so we've got the detection array, we've got, an avalanche diode, single photon, wow. Non-volatile RAM memory, RAM, ROM, got the microcontroller. So it is a microcontroller of its own, advanced ranging cores, the VCSEL driver, I don't know what that is. Custom manufacturing calibration flow. Now, does that mean I'm going to calibrate it, or does that mean somebody's calibrated it before mounting it on a board for me? Power on, power up, and boot sequence. Okay, that could be interesting. So there are 2 options available for device power up. X shut pin. So this option helps to optimize power consumption. Completely powered off when not in use. Okay. So you could perhaps, if you have multiple things on the Pi, power these down if you're just not using your ranging sensors. Could be handy. Ranging sequence, API initialization, start ranging, get ranging. Interesting they talk about API here. Is that just when you set certain things in the register or what? I2C interface, control interface. I don't see any addresses. Maximum speed. Device address of OX52. Right, okay. Now this is one problem I was aware of, which is that actually all of these ship with the same address. And my understanding is you can't get them to program that address into some non-volatile memory. Despite the block diagram showing non-volatile memory, perhaps for calibration data, I2C addresses wasn't one of the things they considered. But what I want to know is what are those register indexes, because that's when we know what our code will need to do. reference registers. Address. Wait, what? Okay, now what I was looking for here is a table to say register where you push a mode, read back data, or something like that. How does this thing actually jive? Plan B. It's my understanding that Adafruit have definitely got libraries for this to make it work with the Arduino and various other things. We can probably go and pick off one of those libraries and work with it. Right, so we download their VLX library. The easiest way to do that is to open up the Manage Libraries menu in the Arduino IDE. Sketch and include library. And we go to Manage Libraries. So if we go All and search Adafruit and it's VL53. Okay, it's this library. You'll be able to install it from the same place on your laptop as well. So if we go to File and Examples, it's right at the bottom. Adafruit. And we got this thing here. And a quick look at this code. So we're setting up, first we're importing this library. We're setting up the device, setting up serial at this 115200 baud rate. Okay, we'll wait until there is serial open. LOX.begin, they're calling it LOX, is actually starting the device, so it's trying to boot it. And it's just going to, okay, fail to boot, and that's a while one, which means the thing will stop there. In the loop part, we've got this sort of VL53LOX ranging measurement data T. So there's a data type for the measure. So we read a measurement, so we tell it to do a ranging test. We've got to pass in this measure, so it fills this structure with data. Measure range status is less than or equal to 4. Okay, so that's less than or equal to... Oh, that's the status of whether we've read the range. So there must be, what, 4 or 5... 5-stage process, I suppose, 0, 1, 2, 3, 4. So if it's not reached the 4th stage, maybe it's gotten stuck somewhere, it's waiting for a response. I guess that might be what happens if you leave the piece of stuff over the top of the lens. So then we print the distance in millimeters, and otherwise we say it's out of range, and we wait 100 milliseconds. And there we are, we've got distance measurements in millimeters. So if I go closer, and we can go below, oh look, and now we're down to my finger's probably not the best thing. Have I got something that's a bit, oh look, I'll use the other VLX. It's saying 20 millimeters. There's no way that's 20 millimeters. This is millimeters, so it might not be terribly stable, I suppose. I was expecting it to be a bit more solid than this. The numbers are all over the place a little bit. So I guess its stability breaks down under what about? Under about 20 it starts to go wrong. And I mean, when we get to the 4 millimeter mark, it doesn't know what's going on. Okay, this is good enough for me for now. Now for a giggle. Let's see what happens if I swap out the sensor. So it's hard to see, but I've swapped out the sensor for one that's still got the film on the front. So we should be getting absolutely silly readings from this, and let's see what we get. So if we open the serial monitor, we're getting measurements. It's not all that. Oh no, yeah. It's way out. Look, that's more than 10 centimeters. So it is way out. So having that piece of plastic there, the protection cover, really does make a difference. Okay, so when you use this, just remember there's a little bit of peely stuff on top that you have to take off before the sensor is usable. Otherwise, you get measurements that aren't entirely sensible. Okay, and finally let's have a look at the code that we're going to use to get the slider display from the VLX sensor. So I've combined the code we're using for the HCSR04 with one single slider with the code we're using for the VLX. And so you've got the slider library, the VLX library, you've got both being set up here as a pair of objects. It begins the Microview, creates a slider, sets up serial. I've left the serial debugging just in case. We do the LOX begin, and again we still do debugging. Now I could perhaps move this across to text on the Microview, but that's just fine. The Microview is already initialized because I've already sent this. Although it says low memory available, it's low memory available, not memory run out, but we'll keep an eye on that. So the main code is still fairly tiny. So again, we're keeping this measurement data T type. We're doing the ranging test in the same way. We've got a distance. We're going to say 1,000 if it reads nothing, but But if it manages to read something, then we're going to say distance. We're going to measure the range in millimeters. We set the value so we get the minimum either of 100 or the distance divided by 10. So if the distance goes above 100, we're going to say that's high enough. Bear in mind that this slider's been set to 100, so if it goes above 100, you can't see anything. And then we display what we've got on the sliders, and we wait 100 milliseconds. So we've now got a display again in in centimeters. Let's have a look at a closer version of that. And there we are. We now have the code running with the VLX and the display showing in centimeters. So I'll get something that's hopefully reasonably reflective. I suppose my hand will reflect laser beams. And there we go. We're at 4, 3, 2. Well, that actually, at this low rating, it's actually much more stable when divided by 10 than it was just straight out. So we go out 3, 4, 5. Now, I was using this, and I wonder if this causes some strangeness because of its type. Yeah, it does, because of the reflectiveness. It might be sensitive to the material type, because my hand can get reasonable measurements. I mean, you can see these going right the way in and out, so that's fine. And obviously 100 centimeters is a meter, and that's beyond my reach. So that seems to be kind of fine, and obviously the responsiveness of this is actually down to that 100 millisecond wait you saw in the loop. That was because otherwise actually it does start to appear a bit unstable at that as well. Okay, so what if I put the pair of them side by side? Let's see if I can make that happen. So I do have more than one Microview, and I've taken out the programming shim from this one, put it on this one. I'm going to need to program this one because I have no idea what code is currently on it. And there we go. The code on there is the demo cube. Okay, so let's go and put my sketchbook, the HCSR04 Microview on this Microview. And that flashing there is it programming. Okay, and this is also in centimeters. So this is a lot less stable. So I'm going to wire across the power line so they're both powered by the same USB port, and we'll see if we can see both together. That's as crude as could be. We've just got a wire going from the 5-volt line there to the 5-volt line there, and from the ground line there to the ground line there. Yeah, they're two different kinds of breadboard. Doesn't really matter. And just trying to find a serial port, a USB port, sorry. And oh, this one's initialized. This one's initialized. Okay, this one took a lot longer. Is that just because it's on the development board? I wonder. All right, now can I see? They're still quite far apart. So maybe if I was to just bend these wires and squidge them together. Hope the wire doesn't interfere. And let's find something like a big paper pad. Big Mod My Pi pad. Awesome. And can I put that where they can both see it and get roughly the same measurement? So look, we've got a 9. Oh, and then this one's out of focus. I'm having a bit of trouble because obviously they're at slightly different depths because this one's still got the programming shim on it. That's not big enough. Okay, this math set looks good. It should reflect both light and sound relatively satisfactorily. And it's a shame I haven't really lined these up in such a way. And you'll note that the front of these cans is quite a way in front of the front of there. So let's see if I can slightly compensate for the fact that I don't know if the measurement of these is from the tip of the can or from the back of the board. So there's a slight, 12. Okay, so there, they're both saying 12. Both saying 9. So the VLX is certainly far more certain of its measurement, calibration or otherwise, than the HCSR04. And the HCSR04, there's a lot more drift in it. Now HCSR04, I've not got the 100 millisecond delay in there, so perhaps the 100 millisecond delay might get rid of some of the flickeriness in that. There is some. So if I go about, where was it? About there, we've got the, yeah, the VLX is doing the same. So I'm just updating the code over here. Ooh. So they've both got pretty much the same thing. Let's try flipping it over where it's got a clear front. Yeah, the VLX is having a harder time with a clear front, kind of. Now, what I'm wondering is, and the other thing is, I can't hear this, but maybe the microphone is picking up clicks from this, because these do click, and some microphones are very sensitive to them. Do I have anything soft enough? Because I suspect if I had the right soft thing, well, both are going to have trouble, because I suppose it's not going to make as good a light reflection as it's also not going to make as good a sound reflection. So they appear to be roughly equivalent. And I suspect the differences between them is now going to be more to do with the convenience of their use. I2C, okay, you've got this library that you have to use, and there's no measures registers. It's not warm or anything, that's good. So I2C, 2 wires, but you may need an additional wire for this XS hut or something, unless perhaps you go down this route. So you have I2C, but then you need this extra pin to say which one of these is live, or you use one of these to multiplex to them. These, you need at least 1 GPI pin per device. Depending on the library, some libraries don't like that. For the Raspberry Pi, this will almost certainly need a resistor, basically to drop the voltage so you don't destroy the Pi with too high a voltage. This won't need a resistor. But obviously it still needs one of these valuable GPIO pins per one of these, or you can do it this way. I don't really intend to use the interrupt mode of this, so I'm kind of, the mode I'm using it now, which is get me a measurement, thank you very much, works on both of these, because actually there's times when I'm requesting a measurement, and if I want continuous measurements, probably what I'd likely do is start a small service and have them in a, I don't know, even then it might be that I'd want to dip into recent averages of measurements as well. So yeah, that kind of works for me. So I think both of them compare fairly favourably. The other thing to bear in mind is you can buy these, I don't know, for £4 or less on eBay from anywhere. These tend to be more like £10, £12, £20. Now, I'm using a Pololu model, there is a SparkFun model, there is an Adafruit model. They've all got the same chip on the front, it's just who's made the carrier board. The carrier boards are all the same, they've all got voltage converters and so on. The I2C is going to probably, I mean, in theory, I2C would mean the programming is going to be, well, you just use the I2C library and things mostly work. This thing, the programming means you've got to kind of do some of these timing calculations and divisions, and these are time sensitive in that you've got to do those calculations, whereas these, if you've got I2C handled in hardware, they'll work just fine. So in theory, the I2C means that the VLX should be simpler to work with. The addressing of multiple ones adds a little bit of complexity. The biggest complexity comes from the fact that there's no simple registers for this, and you've got to use their library. Now, normally when dealing with I2C devices, you've got someone's library, and as long as this library is friendly enough to let you get other devices on the I2C bus, that's great. If their library completely hogs the bus, that's not so great. So we have to see how friendly it is with the bus, especially on the Pi, where I'm going to want to maybe chain a bunch of I2C devices together. Whereas this one, you've got to deal with various timings, you've got to deal with a voltage drop on the Pi that this one doesn't have. They can both be used in multiple things. I think the biggest differentiation between the two is the pricing. So £3 or £4 a piece or less on eBay. £10 to £20, and you can get them from various places. So this is a Pololu carrier board. There is a SparkFun one, an Adafruit one. They're all pretty good, to be honest. They all come without their headers soldered on, so you've got to solder the headers on. And I mean, I guess this one is just a pricier thing to play with. Is it worth the step in price from one of these to one of these? Depends on the problem you're trying to solve. I suppose if you don't want the additional components needed for the resistors here on the Pi, maybe. If you want a reduced amount of space, because these are much smaller, that might be a reason. This doesn't necessarily simplify the wiring if you need the extra GPIO pins, or if you decide to opt for one of these big multiplexers, which we'll play with at some other point in time. In terms of stability, there's swings and roundabouts. They're both pretty good, and they're both good enough for when you're kind of doing a robot thing and trying to detect if something is close. If you wanted to replace your laser ranger that you went and bought from a DIY store, I'd recommend neither of them with your own code, because they would have been properly calibrated in a way you just do not have the materials to do. So I hope you've enjoyed this investigation of the VLX time of flight sensor versus the HCS R04 ultrasonic sensor. You've seen a bit of the code. You've seen, well, we've got a demonstration right here of both of them active at once. And if you want to see more of this, please subscribe and come back to my channel. Please ask me questions. Maybe I can do more sessions with them. And don't forget, go make stuff and be awesome. See you next time. Bye!